All right, we are going to look here at how a system that's in equilibrium reacts to certain changes. So equilibrium tends to provide stability. Equilibrium, we don't talk enough about it. It comes at the end of chemistry, but it's really important in the world around us and in our biological systems. Local systems, global systems in equilibrium, they limit temperature change in the air, pH change in the soil. They've slowed the buildup of carbon dioxide in the atmosphere to much less than it would be otherwise. Equilibrium in our bodies and our cells contributes to homeostasis. You learned about that in biology, the maintenance of constant conditions of temperature and concentration of cell components. In this lesson, we are going to analyze a reaction at equilibrium and see how it responds when we add one component. Spoiler, it's going to tend to make things stable. We will then express a principle that summarizes how systems at equilibrium respond to changes. And finally, we will apply this principle to predict the responses of different systems to changes in amounts of substances, temperature, and pressure. So our learning targets: analyze a system at equilibrium to predict how it will respond when more of one component is added. Understand that LeChatelier's principle gives a shorthand for predicting how systems at equilibrium respond to changes, and then apply LeChatelier's principle to predict how specific reactions will shift in response to given stresses. So recall reaction rates and reversible reactions. Reaction rates are higher when the concentration of reactants is higher because the frequency of collisions goes up with the concentration. If we consider a reversible reaction, the forward reaction is fastest at the beginning when the concentration of reactants is highest, and it decreases as reactants get used up. The backward reaction is slowest initially. It is initially zero because there are no products at all, and it increases in speed as the products build up. Remember, the backward reaction is products reacting together to go back to reactants, so you need products for that to go. The higher the concentration of products, the faster it goes. So recall, equilibrium is reached when the reverse reaction builds up and the forward reaction decreases to the point where they are equal. From then on, we have a mixture of reactants and products whose composition doesn't change. All right, equilibrium constant. For every reaction, a generic reaction is written little a of A plus little b of B goes to little c of C plus little d of D, balanced chemical equation. This ratio, products over reactants, looking at the concentrations of the products, and they are raised to powers, which are their coefficients in the balanced chemical equation. This ratio is a constant. We call it the equilibrium constant, KEQ. Every reaction has one of these constants. For every reaction, doesn't matter what proportions you mix, two or more different reactants plus some amounts of products if you want together, the reaction will continue until the products and reactants are in this ratio. And then, of course, the reaction continues. You learned in the last lesson that both reactions are continuing, but there is no further change in concentration. The concentrations are constant and the rates are equal. All right, no matter how much of each component you start with, you end up with this ratio of concentrations equaling the same value, the equilibrium constant. Let's look at a specific reaction. The reaction to manufacture ammonia, NH3, from nitrogen and hydrogen, called the Haber process. N2 plus 3H2 goes to 2NH3. That's balanced. The equilibrium constant at 25 degrees Celsius is 6.4 times 10 squared. So KEQ equals 6.4 times 10 squared equals this expression, which if you look at it carefully, you'll see it is made from the balanced chemical equation applying that rule, products over reactants, concentrations raised to the power that is the coefficient in the balanced equation. All right, let's look at what happens if we add some hydrogen to this equilibrium mixture. So here, this shows hydrogen is a reactant. Here, this shows where hydrogen appears in this expression. What is this going to do? What is adding hydrogen going to do to the value of this expression? it's going to make it smaller, larger denominator. It's going to make smaller than the equilibrium constant. It is not equal to the equilibrium constant anymore. It is less than the equilibrium constant. So what does a mixture that is not at equilibrium do? Well, the forward and reaction both go. One will be faster than the other until equilibrium is reestablished. Got ahead of myself. What is going to happen to this reaction mixture? We have said that the reaction will always go until this ratio equals the equilibrium constant KEQ. The ratio needs to increase because this denominator is bigger. The ratio decreased, so the ratio needs to increase to reach KEQ. What does that mean for reactants and products? The ratio will increase if we get more products and less reactants, because products are on top and reactants are on the bottom. That means if this forward reaction is faster, making more products faster than making reactants, it'll net use up reactants and make products. So the product ammonia will be formed faster than it is used up temporarily until a new equilibrium is established, and this ratio is once again equal to KEQ, the equilibrium constant. We say the reaction shifts to the right or shifts toward products. Let's look at what happened to the reactant we added, hydrogen gas. Since the forward reaction was faster than the reverse reaction temporarily, more hydrogen was used than was reformed. So we dumped in a bunch of hydrogen gas, and the reaction responded with a net conversion of hydrogen to products. The reaction reduced hydrogen. We added hydrogen, and the reaction made hydrogen go away. The same thing will happen anytime we add one component to a reaction that is at equilibrium. Adding a component will temporarily change the value of the ratio, products raised to their powers over reactants raised to their powers, so that the system is temporarily not in equilibrium. The reaction that uses up the thing that we added will speed up temporarily, using up that component. Not using up all of it, but using up some of it. In short, we do something to a system in equilibrium, and the system responds by undoing the change. The system will be similarly contrary if we take away one component. Let's look at the Haber process again. So we have nitrogen plus 3 hydrogen making 2 ammonia, 2 NH3. And the equilibrium constant expression has ammonia in the top squared over nitrogen. These are concentrations, concentration of nitrogen times the concentration of hydrogen cubed, since hydrogen has a coefficient of 3. Suppose we have a way to remove some of the product by condensing it or reacting it with something. And this is something that people do. We want to make the product. We want to pull the equilibrium so we can remove the product. So what will happen if we remove some product? Now the numerator in our ratio has decreased, right? The reaction is no longer at equilibrium. This expression was equal to some constant, but we took a bunch of this away. Suddenly this number is less. This ratio no longer equals the equilibrium constant. To get to equilibrium, the reaction will have to make a net increase in the numerator, an increase in product, which is a shift to the right. We could say that since there is less ammonia present, there are fewer collisions of ammonia molecules, and so the reverse reaction must slow down. So that means the reverse reaction is not as fast as the forward reaction, and that leads to buildup of product. So the reaction replaces the substance that we remove. Once again, the equilibrium system responds so as to undo the change that we made. In this case, it is a good thing because we induced the system to make more of what we want, which is ammonia. All right, LeChatelier's principle. LeChatelier was a chemist, and he came up with this overall principle. He said, when any system at equilibrium for a long period of time is subjected to a change, the system changes to a new equilibrium, and this change partly counteracts the applied change. I skipped over part of that. There are several changes that can be undone by a system at equilibrium. I'll read it again. When any system at equilibrium for a long period of time is subjected to a change in concentration, temperature, volume, or pressure, the system changes to a new equilibrium, and this change partly counteracts the applied change. So this is really powerful. All these changes can be offset. Change in temperature. This is where we get the temperature stability of the world. There are equilibria that involve taking up energy and releasing energy. And if the temperature starts to change, those equilibria shift to offset the change. If it wasn't for that, the Earth would be uninhabitable because of the wide temperature swings. Volume, changing pressure, equilibrium reactions can shift to undo the change. As commonly stated, and this is the way we usually say it in chemistry, when a stress is applied to a system at equilibrium, the equilibrium will shift in the direction that relieves the stress. I don't think this is very helpful wording, but this is the way it is usually expressed in chemistry, so you need to be familiar with it, and you need to understand that when they say a stress, they are talking about a change in concentration or one of these other things, a change in temperature, a change in volume, or a change in pressure, and that if the system has the ability to shift one way or the other to offset and relieve, undo that change, then it will. So this brings us back to the idea of stability. A system in equilibrium can shift one way or the other, temporarily speeding up or slowing down one of two opposing reactions until a new equilibrium is reached. The direction of shift is always the direction that counteracts the change. Let's apply LeChatelier's principle. Consider the reaction 2 sulfur dioxide, SO2, plus oxygen goes to 2 sulfur trioxide, SO3. Oxygen is a diatomic, remember. Which way will the reaction shift if we add more sulfur dioxide? SO2 is a reactant. So the system will respond to reduce the concentration of SO2 by shifting to the right, using up the sulfur dioxide. Let's look at the other chemical species in the reaction. If the reaction shifts to the right, using up sulfur dioxide, what will happen to the concentration of the product, sulfur trioxide? Well, we're making more of it. So a rightward shift means more reactants getting converted to products. So that means the new normal has a higher concentration of sulfur trioxide, SO3, the product. All right, what happens to the concentration of oxygen, O2, after sulfur dioxide is added and the equilibrium shifts to the right? Well, that oxygen is going to react with sulfur dioxide. When the forward reaction speeds up and there is a net conversion of reactants to products, the concentration of oxygen must decrease. So we're going to end up with less oxygen than we had in the first place before we added the extra sulfur dioxide. LeChatelier's principle does not mean the previous conditions are restored exactly. It means that if the system can partially undo a change by means of a shift in equilibrium, it will. All right, let's review the learning targets. If you feel you have not mastered one of these learning targets, I do want you to watch the video that I'm going to post after this, but if you watch that and you feel that you have not got one of these learning targets, I would ask that you go back over this and especially concentrate on the analysis of the Haber process and how things changed and why we believe that the equilibrium shifts in the way it does based on the change in the ratio of products to reactants. So they were analyze a system at equilibrium to predict how it will respond when more of one component is added. Understand that LeChatelier's principle gives a shorthand for predicting how systems at equilibrium respond to changes, and apply LeChatelier's principle to predict how specific reactions will shift in response to given stresses.